Welcome back. Hello. Hope you've had a good week. So last time we were dealing with this issue of protecting groups, which we're going to finish up real quickly today. The idea behind a protecting group is it's something you do in organic chemistry when you want to do a reaction, but another functional group in that molecule is going to interfere with your reaction. This is one such example, trying to add an organolithium reagent to a carbonyl oxygen in the presence of an OH group. Not going to happen because the organolithium reagent is so basic that you would deprotonate the oxygen before you even got close to the carbonyl carbon. So the idea is we're going to do something to the problematic functional group, in this case an alcohol, that's going to get rid of the problematic acidic proton. But our strategy has to be easy to install. We're going to use a protecting group. It's going to be easy to install and easy to remove. Here's the strategy. First, protect. The OH goes to something that lacks the key functional group that's causing a problem. Then we do the nucleophilic addition step. Then we do the deprotection step and unmask that alcohol. In the end, it looks like we were able to go straight from here to here without a problem. Only we know we did a little sidestep. And so that strategy is used a lot in organic chemistry. We're going to present just one protecting group today, but you'll encounter others soon. The alcohol protecting group, or the protecting group for alcohols, is what's called a silyl ether. Silyl stands for silicon. Ether is what you'd have if an oxygen's bonded to two carbons. But in this case, one of those two carbons is actually going to be a silicon. That's reasonable because silicon-oxygen bonds are decently strong and because silicon's from the same row, same column of the periodic table as carbon, so it's reasonable to form a silyl ether. Here is an example of a silyl ether. So if we could replace the proton with instead a silicon, and this is the example of the silyl ether that your text uses. There are tons of silyl ether protecting groups, but this is the one that your text uses. And it's called a tert-butyl dimethyl silyl ether. Now, because we get tired of saying that, and because we even get tired of drawing it, organic chemists use an abbreviation for the silyl ether. You just draw the oxygen and then you use the acronym TBDMS, tert-butyl dimethyl silyl ether. That's the protecting group. So, and you'll notice that it lacks the acidic proton on the oxygen, and the oxygen-silicon bond is decently strong, so it can withstand having the nucleophile be attacked, having the organolithium or cuprate the organolithium or Grignard reagent attack the carbonyl carbon. So now we need to talk about what the protection reaction is. You start with your alcohol, and this reaction is basically just a substitution reaction. The oxygen is the nucleophile. The electrophile is the silicon, and it's got a leaving group on it. So because silicon is sort of analogous to carbon, what we're doing here is basically analogous to a substitution reaction from 351. If this were a substitution reaction, you'd say, oh, look at that tertiary carbon. In this case, it's a tertiary silicon, and you might predict, oh, the leaving group, sorry, excuse me. You might predict something about whether the mechanism should be SN1 or SN2. Silicon's bigger than carbon, and so it's not as constrained by steric issues as carbon is. We will not worry about the mechanism of this substitution reaction at all, excuse me, other than to draw what the product is. If you've noticed, to get to the silyl ether, we need to make an oxygen-silicon bond, and the proton's got to go somewhere. We're also going to need a base. This is the thing that's going to remove the proton from the oxygen. We're going to use a mild base that's not a really good nucleophile. I'm going to draw it for you here. It has a name. It's called imidazole in your text, and that is because that is its name. So that works, only I've drawn it wrong. The double bond should have been here. We'll come back to imidazole later on in the class when we learn something about aromaticity. The basic nitrogen is this one, the one that's doubly bonded and has a lone pair. After we do the reaction, and this reagent, by the way, you can abbreviate as TBDMS chloride, that gives you the protected silyl ether. Okay? At that stage, then, after you've done protection, you can do the nucleophilic addition step. That's where we add our organolithium or Grignard reagent. And then after aqueous workup, we get our tertiary alcohol product. Then we need to do the deprotection reaction. And again, this is going to be a substitution reaction, but it's going to involve using fluorine as the nucleophile. So just for fun, I'm going to draw out the tert-butyl dimethyl silyl ether so we can see it. It turns out that even though silicon-oxygen bonds are decently stable, silicon-fluoride bonds are even more stable. So what we want to do is do a substitution reaction where now the fluorine is the nucleophile, the oxygen is the leaving group. Fluorine's going to make a new silicon-fluorine bond, and then the oxygen will be able to leave. And as the oxygen leaves, it's going to pick up a proton, probably from some source, probably on aqueous workup. We won't worry about that because your text doesn't. F minus is the nucleophile here. It's not particularly soluble in organic solvent, so you need a counter ion that will help it be soluble. The counter ion of choice is actually a nitrogen-based counter ion where the nitrogen is bonded to 4 alkyl groups. That's called a quaternary ammonium ion, and together with fluoride forms a quaternary ammonium salt. The alkyl groups on the nitrogen help the fluorine be soluble. This reagent is called tetrabutyl ammonium fluoride, or TBAF for short, so it's alphabet soup today. But again, that is fast and easy removal of the silyl ether protecting group, and it's driven by the strength of the silicon fluoride bond. Okay? Sorry? TBAF stands for tetrabutyl ammonium fluoride. That's just the abbreviation for the name of the molecule that I've drawn up here, this quaternary ammonium salt. Okay, so that's your first protecting group strategy. You'll need a little bit of practice on that. Go ahead and do some problems on that. Make sure you can do that. All right, so what we will do now is move on to chapter 14, where our theme is going to be reactions of nucleophiles with aldehydes and ketones. Only our nucleophiles are not going to be as strong as the organolithiums or the Grignards or the cuprates. So we're going to return to this question that we've asked before for an aldehyde or a ketone, which is it reasonable for the nucleophile to attack the aldehyde directly to get a tetrahedral intermediate like this? To ask that question, we will essentially be comparing the nucleophilicity of the nucleophile versus a negatively charged oxygen. And it's possible that sometimes we'll see that we have a nucleophile that isn't strong enough to attack directly. And in those cases, we might potentially have the need for acid catalysis. And what do I mean by acid catalysis? Well, you might envision one option. Supposing you had a nucleophile and you decided that this nucleophile was way less reactive than a negatively charged oxygen. So you predicted that this step here would not be reasonable. Then you could imagine doing the following. starting with the carbonyl compound and adding an acid catalyst. In this case, the carbonyl compound would now be a nucleophile, so lone pairs, the highest energy electrons in the molecule, lone pairs on the oxygen, would deprotonate the acid, and you would get this oxonium ion intermediate. And hopefully you can see that that oxonium ion should be more electrophilic than the starting material. The reason for that is, of course, I can draw a resonance structure of the oxonium ion in which the positive charge that's on the oxygen is actually on the carbonyl carbon. Protonation of the carbonyl oxygen makes the carbonyl carbon in the oxonium ion even more electron poor. So at this stage, then it becomes more reasonable for your nucleophile to attack and generate your intermediate that looks like this. All right.
What does SM stand for?
Sorry, SM stands for starting material. More electrophilic than the aldehyde. Okay. So that's one way that you could envision an acid helping a nucleophilic addition step to happen. We've never had to do that so far because, of course, our nucleophiles have been totally fine to attack directly. If your nucleophile is an organolithium or Grignard reagent, it's way more reactive than a negatively charged oxygen. So that first step, you're good to go. This first scheme for acid catalysis involves multiple steps. We protonate the carbonyl oxygen first, then we do nucleophilic attack. And that's one way you can imagine the reaction happening. When it happens when acid catalysis does this, when the acid protonates first and then you get nucleophilic attack, that's called specific acid catalysis. We won't encounter that term a lot in this class. You will encounter it in biochemistry, so I wanted you to be exposed to it here. And all it means is you protonate first, and then in a separate, slower step, the nucleophile attacks the carbonyl carbon. Okay? So that's one option for acid catalysis. Option 2 for acid catalysis is we protonate while the nucleophile attacks. So you could imagine a situation like this where you have the same aldehyde. Here is a nucleophile, and the nucleophilic attack and the proton transfer all happen in the same step. So nucleophile attacks the carbonyl carbon. We break the carbon-oxygen pi bond. At the same time, as negative charge is building up on the carbonyl oxygen, the lone pairs on the carbonyl oxygen remove a proton from the acid, and then we go directly to this intermediate. Okay? That kind of scheme all at once is called general acid catalysis. And a lot of enzymes do this. They'll have nucleophiles attack at the same time as you're transferring a proton. Okay, questions? Yeah?
How would you ensure that the nucleophile doesn't just deprotonate the acid?
Yeah, that's a really great question. How do you prevent the nucleophile from just deprotonating the acid? And what you're getting at is this issue of sometimes it will matter how acidic your acid is. For reactions like this, one of which we will talk about today, it's called imine formation. People have run the reaction over a range of pHs, which is the same thing as trying multiple acid strengths. And there's a bell curve. There's a sweet spot where your acid is strong enough to protonate the carbonyl oxygen but doesn't interfere as much with the nucleophile. You go more acidic than that, you start to protonate the nucleophile, and that's a problem. You go less acidic than that, and you don't protonate the carbonyl as efficiently. So yeah, there is a sweet spot. Enzymes are pretty good at doing that, though. Others? Yeah?
What are the conditions to generate specific versus general
Great question. What are the conditions to generate specific versus general acid catalysis? You could imagine a couple of things mattering. First, the nucleophile. If the nucleophile is really strong, you might think, or stronger on the stronger side, you might think it's not going to wait around for the acid to protonate first, it's going to attack during. If the nucleophile is weaker, it might need to wait for the acid to protonate first. So we will see for examples in this chapter, we will see that specific acid catalysis generally involves weaker nucleophiles like water or alcohols. Whereas general acid catalysis is going to involve slightly stronger nucleophiles like amines. You could tell that an amine is more nucleophilic than an alcohol or water, even though they're all neutral, a couple different ways. Draw the conjugate acids and compare their pKa's, or just remember that nitrogen's less electronegative than oxygen, which literally means that the electrons, lone pairs on nitrogen, are higher in energy than lone pairs are on oxygen. So we'll see the stronger nucleophiles like the amines tend to attack while protonation is happening, whereas water and alcohols tend to wait for protonation to happen first. The other thing that you could imagine deciding between those two is just the strength of your acid. If your acid's super strong, maybe it protonates fast. That won't be a decision point. And as I said, we're going to learn mechanisms for using amines as nucleophiles, and we'll learn a related but specific acid catalysis mechanism for water or alcohols acting as nucleophiles. Good, other questions? So let's dive into the amines. The reaction we're going to do now is called imine formation, but I want you to keep in the back of your mind that the reverse reaction of imine formation is called imine hydrolysis, and we're going to learn that too. But it turns out they're just two sides of the same coin. So if you know one, you should be able to figure out the other. Here's imine formation. So you start with your aldehyde or your ketone, and then we'll use a simple amine. And then you need an acid catalyst. So before we draw the mechanism, let me just mention some good acid catalysts for imine formation. Some that you will see. One is just acetic acid. It's not terribly acidic, it's a weaker acid. It has a pKa of 4. Another is a much stronger acid that you saw in 351 called paratoluene sulfonic acid, and its structure looks like this. Either of those are fine. There are some other acids, but yeah. One potential issue that I've seen students struggle with before is if this is drawn as the acid catalyst and this aldehyde is the starting material, some students get distracted by the fact that both of them have carbonyl oxygens, and then suddenly they're like, what do I do with that? Remember that aldehydes are at the top of our list of reactive carbonyl compounds. Carboxylic acids are different. They're not really electrophilic at the carbonyl carbon because they're so acidic at the proton. So if a nucleophile or a base approaches a carboxylic acid, the first thing it's going to do is remove the proton, not attack the carbonyl carbon. So you'll have to get accustomed to that and not be distracted by the carboxylic acid as an acid catalyst in imine formation. Okay, so what I'm going to draw for you here for imine formation is different than is drawn in your text, and I'll explain how. Yes? Right, why can sulfur have more than 4 bonds? That's sulfuric acid does too. The octet rule really holds only for first and second row elements. As elements get bigger, they can tolerate more bonds. Yep. Yes?
Say you wanted to do a reaction with acetic acid at the carbonyl carbon. Could you use a protecting group on that?
Great question, great preview. Yes, in chapter 16, what we're going to do, it's not exactly using a protecting group, but we will have to deal with that proton. So one strategy for doing chemistry with carboxylic acids is to first convert the OH into something that's a good leaving group, and then you're off to the races. Yep. Okay. So I will show you the mechanism for imine formation that's physically realistic, and then I'll explain how your text differs from that. We'll go with my mechanism because, hey, it's my class, right? I can do whatever I want. So what happens is the nitrogen attacks the carbonyl carbon, attacks the pi star at the carbonyl carbon at the same time as the carbon-oxygen bond is breaking, at the same time as lone pairs on the carbonyl oxygen are removing a proton from the acid. I'm using equilibrium arrows because this first step and all of the steps in this reaction are what we call reversible, meaning the forward step is reasonable, but so is the reverse step. I'm going to use color shading to sort of help us keep track of things. This is our amine nucleophile, and in pink I'll use the carbonyl oxygen. And I want you to notice how this general acid catalyzed step allows us to go directly to this intermediate. Notice that when the amine is now attached via a carbon-carbon bond to what used to be the carbonyl carbon, it has a positive formal charge on it. And notice that the oxygen, what used to be our carbonyl oxygen, is a neutral OH group. Now right away we can pause and see how general acid catalysis has made this nucleophilic attack step reasonable by comparing that with the alternative that's shown in your text. I'm going to erase this in a moment, but this is the first step that's shown in your text. Nucleophile attacks carbonyl carbon to get a negatively charged tetrahedral intermediate on the oxygen with a positively charged nitrogen here. That's the first step that's shown in your text. Now, here's why I'm uncomfortable with that, and I think you should be uncomfortable with it too. Starting with the text, we ask, is this nitrogen nucleophilic enough to generate a negatively charged oxygen? To make that comparison, draw the conjugate acid of your nucleophile, which is this ammonium molecule. It has a pKa of around 18, and we use conjugate acid pKa's to rank reactivity of bases or nucleophiles. Then look at this negatively charged oxygen. Its conjugate acid should have a pKa, is an alcohol, which should have a pKa of 16. Basically what these tell us is the negatively charged oxygen is more reactive or higher in energy than the amine starting material, which means it's probably, in my mind, not that reasonable to attack directly. Go ahead.
Was the pKa of the ammonium 18 or 11? You said
11, it's 11. Yeah. I'm gaslighting you. I wrote 11, but I said 18. Yeah, sorry about that. My apologies. The pKa of this ammonium ion is 11. Yep. So that's why I'm kind of uncomfortable with this step. And I'm not sure how to draw that discomfort other than not great. Okay? Your text will do that because it's simple, but it's actually not that great a reflection of reality. So I'm going to just scoot this over here in the notes and pull this down here so I have more space. What I'm showing you here is more realistic. Okay? And this is why you actually come to a university and listen to someone talking to you rather than just read a textbook on your own, because there's nuances that you can get. And sometimes the professor will tell you that 18 is 11, and then, yeah, you get to have some fun. So, now, look at the intermediate that we've made. I told you this reaction's reversible. What I mean by that is it's totally reasonable for a neutral oxygen, for lone pairs on the neutral oxygen technically to be correct, the reverse step would look like this. The conjugate base of our acid would remove a proton from our alcohol at the same time as electrons would kick down and the leaving group would leave. And it's totally reasonable for a neutral oxygen to kick off a neutral amine as a leaving group. So that step can go forwards and backwards. Students are generally uncomfortable with that when they first encounter reversible reactions, because all you want to know is, what do I do on a test? And when there's multiple things that are true or reasonable, you're like, what if those are both options and I'm supposed to pick between them? Don't worry about that. Right now, our goal is to get a feel for what's going on in these reactions, and I will actually draw for you the reverse mechanism of this reaction as well, because that's what I told you is the new reaction, imine hydrolysis. Okay, instead of doing that, let's think about, what if this conjugate base, instead of going back, removed a proton from the nitrogen, which is positively charged. If that happened, that would get us to this intermediate, which is neutral. And one interesting thing about this neutral intermediate is suddenly that neutral nitrogen is way less good of a leaving group than it was before. Right? If I just mentioned that when it's positively charged, it could leave as the neutral amine, and that's totally reasonable. When the proton is gone, it would have to leave as a negatively charged amide conjugate base, and those are terribly unstable. So we're using actually our acid catalyst, and I guess I'll label the acid in green, because in the cartoons acids are always green, even though basically no acids are green. We're using the conjugate base to sort of trade around who's a good leaving group. So we stop the nitrogen for being a good leaving group. This intermediate is called the carbenolamine. And from this point on, our mechanism is basically going to be the same as is shown in your text. All right, so we've regenerated our acid, which is good because it's a catalytic reaction, so we have to not consume our acid, or if we consume it, we have to regenerate it. Now you've got lone pairs on the oxygen that can remove a proton from the acid. Of course, this is reversible, meaning the conjugate base of our acid could turn around and steal its proton right back. Okay, and here is the conjugate base of our acid. Here in purple is the nucleophile that we originally added. And by protonating that OH group, we turned it into a good leaving group. And one of the things here is that this neutral nitrogen is now a decent kicker-offer. So even though the players are different, what we're going to do next is an elimination step like we saw before in the previous chapter in carbonyl chemistry. Anytime you have a decent leaving group on the carbon, lone pairs on the adjacent atom can kick down and the leaving group can leave. So I'll draw the arrow this way, and here is water after it left, and then here is the nitrogen. And then here is our acid catalyst. Okay, in that step, water was our leaving group. Nitrogen's here, conjugate base is here. This intermediate is called an iminium ion. It's the conjugate acid of our final product. And to generate that final product, we remove a proton from the nitrogen. And that will get us to the final product, which is an imine. I've drawn it in this way just to keep everything oriented in the same way relative to what our starting materials were. But, of course, you are welcome to draw the imine like this if you want to draw it right side up. Okay. And here we have to, worry a little bit about pronunciation because if we say amine, because in the United States English we like the schwa, so that's the sound, the amine. And then the product is an imine, the short I sound, imine. I is for imine. Somebody write a children's book called I is for imine. Okay, questions about that? One thing to point out is that I said that all of the steps are reversible. One of the ways you can make the reaction go forward is to take advantage of Le Chatelier's principle with water, and you simply remove the water. And there's a lot of strategies for doing that in the lab. Some of you that take the 353 lab may have already encountered this. There are some inorganic salts that are they are hygroscopic, meaning they absorb water. Calcium chloride, magnesium sulfate are examples of these. You can put those in your reaction mixture and it will soak up water that's formed, and that will help drive the reaction forward. Yeah?
You said that it's like the same players, but it makes the nitrogen is a proper. Can you explain how since nothing happens to the hydrogen?
The same players, but the nitrogen is, and then I missed the word. Say it again.
Like, how does it kick off the water? Is it just because it's water and it just pops off?
Right, so what you've got here is a carbon that has a good leaving group attached. Maybe we should switch the color to yellow. And then the nitrogen has lone pairs on it, and that's going to be the kicker offer. So what made those carbonyl elimination reactions happen originally wasn't that the oxygen, it had nothing to do with the oxygen, it had to do with the lone pairs on the oxygen. Whether it's on oxygen or nitrogen is fine. As long as you have lone pairs adjacent to a leaving group, you can be in this elimination kick-offing situation. Yep, yes?
You said removing water pushes the reaction forward. If you added water, would it push it backwards?
Exactly. If you added water, would it push the reaction backwards? Yes. So for imine hydrolysis, if you wanted to hydrolyze an imine, can't spell hydrolysis, can we? And that Y is wonky, sorry. Imine hydrolysis, you would start with the imine, and then you would use an acid catalyst in an excess of water. You would use probably just any, like HCl or anything that has a lot of H3O plus in it. And that is going to hydrolyze your imine back to the aldehyde or the ketone. Pay attention to what the R groups are on the carbonyl carbon. And then the amine will come off, and under acidic conditions, it'll probably be in its ammonium form. Yep. Okay, others? Yes?
What's the pKa of the amine in the, when we have the water, before the elimination?
All right, so yeah, what you want to do, if you want to see, is this reasonable? Can a neutral amine kick off water? You would compare the pKa of the neutral amine versus the pKa of the, you would compare the pKa of the conjugate acid of the neutral amine, which is an ammonium ion, pKa 18. No, sorry, it's 11, versus the pKa of the conjugate acid of the leaving group, which in this case would be H3O plus minus 2. Yeah, totally reasonable. Yep. Okay. So I mentioned the reaction's reversible. What I've typically done in previous semesters is say, okay, go home and figure it out. And there was pushback because people doubted their abilities to figure it out. I have confidence in you. I think you could figure it out. But let's do it together once, shall we? So the secret for reversible reactions is you don't have to memorize or try to remember any new intermediates. In fact, as you will see, we can draw a mechanism for this reaction. Some of you that are on pen and paper are going to hate me for this, but I'm sorry. We're going to do a great big copy and paste. No, and then what I'm going to do is I'm going to erase the arrows. Some of the arrow erasure is destroying some of the highlighting. We're going to erase the arrows. We're also going to erase some of the color commentary here. So one of my callings is I do music at Special Needs Mutual. I used to be a primary chorister, but I think the kids were too rowdy, so I was sacked from that position. Not really, I was released after 3 years, so I suppose that's not being sacked in disgrace. But anyway, at Special Needs Mutual, I do music, and they're doing a talent show next week. And one of the participants is going to do, he's going to read his sportscasting. He summarized the NFL playoffs for the last week, and he's going to read it to us because he really, really enjoys sports. I offered to do color commentary. I was like, well, you know, Steve, the way you win football games is you got to get out there and score more points than the other team. You can't win football games if you have turnovers or can't get first downs, right? I know nothing about sports, but I'm doing pretty decent color commentary there, aren't I? Okay, well, speaking of colors, all the colors are intact there. That was a smooth segue. Anyway, there's our reverse reaction. We're going to be doing imine hydrolysis. And all of the intermediates are going to be exactly the same. We're just going to, and in fact, if you know what the intermediates are and you have a sense for what's reasonable in reactions, the intermediates are the instructions for what the arrows have to be. For example, we start with the imine and our acid catalyst. The next step, if we're going backwards, is start here and here. The next step is we form the iminium ion. So you tell me, what are the right arrows for making the iminium ion? Right, lone pair on the nitrogen to the hydrogen on the acid, and then, yeah, we do a deprotonation reaction. And check yourself and see, did those arrows lead, are those arrows the instructions for drawing this intermediate? Good, okay. Iminium ion, what are we gonna do there? This is a stage at which some people get confused because they're not totally sure what to do with iminium ions, and they're not totally sure what to do with water, and in fact, they may have forgotten that water was even there. Look at the previous intermediate from imine formation. There we have the neutral nitrogen, positively charged oxygen on the same carbonyl carbon. How do we get from the iminium ion to there? What's the right thing to do? Lone pairs on oxygen attack the carbonyl carbon. We can think of imines as having similar reactivity to carbonyls. So in my mind, I don't look at the imine and I say, oh, I have no idea what that even is. I say, that looks a whole lot like a carbonyl. Only difference is we got nitrogen instead of oxygen, okay? So we attack the carbonyl carbon, we break the pi bond, electrons move out to be a lone pair on nitrogen. Check it, if we got the right connectivity based on those arrows, sure, okay? Now, how do we get from here to the carbanolamine? What do we do with the conjugate base of our acid? Just take the proton off, right? Then, if we want to get from the carbanolamine, and remember, at this point, having a sense for strategy and endpoint is useful. Our goal is to get back to the aldehyde. We're going to have to kick off the amine as a leaving group. In the carbanolamine, the amine is not a good leaving group, so one of the things you can do to make that happen is you use your acid catalyst to protonate the nitrogen, thereby turning it into a good leaving group here. At this stage, you have to do what, at this stage we would do the reverse step of what was done in imine formation. So we're going to have the conjugate base of our acid pull the proton off of the oxygen at the same time as the oxygen is kicking off the amine as a leaving group. And there we are at our starting point. Okay, that's the reverse reaction. And as you've seen, we didn't even have to draw any new intermediates. We just had to push the arrows backwards. Now, your challenge is, in the very near future, perhaps next time, we're gonna do a reaction called acetal formation. It's gonna be almost the same as imine formation with a minor detail later on. I am not gonna show you acetal hydrolysis in class, though it is in your textbook. I'm gonna leave it to you to do exactly what we've done here and push the arrows backwards, okay? Because you can do it. All right, there's some interesting things we could say about imines that we ought to pause and do. Anybody out there in food science, nutrition, okay? Anybody like baking? When you bake something, anyone like eating baked goods, right? More hands there. When you look at a recipe, you're making cookies or something, you're supposed to bake until what? Golden brown. Those are the magic words. So bake until it still starts to have a golden brown color. Well, what's going on there? It turns out the baked goods have a couple of things in them usually. You have carbohydrates, and then you have some protein, usually gluten from the flour, some other kind of protein from the flour. Carbohydrates have aldehydes in them. So I'm drawing for you now glucose. And I'm going to draw it for you in its 6-membered ring closed chain form that within a day or two you will learn to call a hemiacetal. But right now you can just think of it as glucose. Glucose is in equilibrium with a small amount of open chain form that's an aldehyde. Everything else is the same, and though we'll talk about this later, you can get a sense for how the closed chain form happens if you think about that oxygen attacking this blue carbonyl carbon as a nucleophile. In any case, this is the aldehyde form of glucose, and as I've said, aldehydes are reactive. That's one of the reasons why you don't want your blood glucose level to be too high, but we'll come back to that in a little bit. In the baking, sort of making stuff golden brown reaction, what happens is proteins have amino groups in them. So this is that's not enough carbons. The squiggly line means the rest of the protein is over here. This is the amino acid side chain lysine. It's a primary amine. And it will undergo at elevated temperature in baking imine formation with lysine, and you will get something like this, where an imine, where the nitrogen of lysine is now forming an imine with the rest of glucose. Okay? That's the starting point for what's called the Maillard reaction, and there are other downstream reactions that happen that create both the flavor and the color associated with golden brown baked goods. So if you bake, you're making imines all the time, right? Another place that imines show up is in monitoring blood glucose level for diabetes. So have you ever heard of HbA1c? Anybody out there heard of that? Yeah? What is that? What is when a doctor wants you to have a blood test to measure your HbA1c, what are they looking for? Yeah.
Indicates your blood glucose over the past month or so.
Right, it's supposed to indicate your blood glucose level for the past 1 to 3 months. Of course, you can get an instantaneous read on blood glucose level with another analytical technique, but sometimes your physician is interested in not what it is now, but what has it been over the past few days. Because all of us are on really good behavior when we go to the doctor, right? We go to the dentist, you brushed and flossed that day. Who knows about the week before? In the same way, a physician might want to know, okay, what's your blood glucose level been over a while? The way they monitor that is they look at your hemoglobin from your red blood cells. Red blood cells recycle, and I don't know what the anatomy is on this. They recycle on the order of every 30 to 60 days or so. I don't know, plus or minus. And red blood cells have a lot of the protein hemoglobin in them. Behold the circular blob that is hemoglobin, abbreviated HB. Some of the amino acid side chains in hemoglobin are lysine. and lysine has an amino group on them, okay? What did you just learn about glucose? Glucose is an aldehyde, or it equilibrates with an open chain form aldehyde. And that glucose can form an imine with your hemoglobin, and the doctor has a way of measuring the extent to which that happens. If you want to know more about that, that's an issue of analytical chemistry and also biochemical assays. But when your doctor's looking for HbA1c, they're really looking for this, and this is called glycated hemoglobin. They have in science, we often have multiple words to describe the same thing. Instead of saying hemoglobin with an imine on it, which is what it is, they call it glycated hemoglobin. Yeah?
So if my hemoglobin forms an imine with my glucose, will I get a golden brown tan?
If you, will your blood be a little more golden brown? I don't know. That's a good question. But it actually turns out that glycation, as with the Maillard reaction, there are other downstream reactions that can happen after imines form. Those are sometimes called advanced glycation end products, and they can be associated with negative physiological outcomes, right? And this is why you want to control blood glucose in diabetes, because if you don't, you're dosing yourself with this really reactive aldehyde constantly, and it's going to be modifying amines in all of your tissues, and it can lead to a lot of the symptoms that are associated with uncontrolled diabetes. Right, and the fact that your red blood cells don't recycle that much means that those individual hemoglobin molecules are getting exposed to glucose over the course of 30 days. So if you measure how much HbA1c you have, that's a decent measure for how much glucose have you had in you uncontrolled over the past little bit. The last thing I want to say about imines, the other place that they show up that's really important is in vision. So you guys can Google this if you want to see a pretty picture of it. I'm not going to attempt to draw an eye or a retina. But in your retina, you have rod and cone cells, right? And inside those rod and cone cells, you have a membrane protein that's called rhodopsin. And rhodopsin is the thing that absorbs the light, and it is also the thing that converts that light absorbance into an electrical signal that your optic nerve can pick up and that your brain interprets as sight. So what we're going to do here is crash course. I have 3 minutes to do it. I'm going to draw a lipid bilayer with the magic of copy and paste. Ooh, thank you. Yeah. Get ready. Are you ready for it? This is the most impressive one. So you'll learn about lipids later. Those are polar head groups and nonpolar tails. This is the membrane protein rhodopsin. It has multiple passes across the membrane. It has a portion that's outside the cell and a portion that's inside the cell. And then embedded here is something that I'm going to call the chromophore. This is the thing that absorbs light. Now, what is that chromophore? It turns out, here is the rest of the rhodopsin protein. Again, it's going to be a lysine side chain, an amino group, that's formed an imine with an aldehyde. And that aldehyde happens to be a highly conjugated molecule, which I'm going to draw here. When we do this, somebody always raises their hand and says, do we have to memorize this for the exam? And clearly I don't really care if you memorize precise structures of biological things unless I tell you otherwise when we get to metabolism and proteins and such. But your goal is to make it appear when you take the exam as though you were in class on that day and were listening. So this is the imine. This is a highly conjugated molecule called retinal. It's so conjugated that the gap between HOMO and LUMO is such that visible light can excite an electron from HOMO to LUMO. That should weaken one of the pi bonds, right? Well, the pi bond that you want to weaken is this one, this cis pi bond, because there's a lot of steric clash between the proton here and the methyl group. When you absorb light, you weaken that pi bond, and then that double bond isomerizes, relaxes from cis, sterically strained, to less strained trans. But imagine what that would do. Here's the other proton that's in the trans position, and you've got to imagine all of this swinging up here, boom, like that, after you absorb light. That knocks some stuff around in the interior of the protein, opens up a channel and allows ions through. That creates what's called a membrane potential, and then your brain interprets that as sight. All of that's been going on the whole time while we've been talking faster than we can talk about, but that's how you see, and an imine is involved. All right, no class on Monday because of MLK Day. I will see you on Wednesday.